who know their software development, but would like to know something a little bit more. So what is vectorization? Vectorization is modern CPUs can process more than one piece of data in the same instruction. So instead of processing one piece of data, it can take 4 pieces of data, like 4 floats, load them these 4 floats to a floating point register that can hold 4 values, and then it can do processing everything on 2, 4, 8 or more elements with a single instruction. So on the left side here you see a loop that you might write in your code, and then the compiler will try to vectorize it to make it faster, to use these vectorization instructions because they're faster. And you see on the right some kind of pseudo assembly that you might get from the compiler. So you see that from address b plus I, we are loading 4 values and putting them to b temp. From address c plus I, we are loading again 4 values, putting them to c temp. Then we are performing four simultaneous loads with one instruction. We're adding together b and c. And finally, we store 4 values to this address a plus I. So this is the essence of vectorization, and everything else builds on top of this. So here is an example how it works in a graphical environment. So I have this 4711, and I'm loading it to a CPU register here. Then I have another value, 3280. I'm loading it to this register here. So these 2 loads are 2 instructions. Then I add them together. That's a third instructions, and I get 4 results. So 4 plus 3 equals 7, 7 plus 2 equals 9, and so on. And then I store the results back to memory. Yeah. So as far as vectorization, this is a technique. So many modern processors nowadays support vectorization. Intel support all x64 processor have some kind of support for vectorization. The whole story started in 2001, then it was developing a lot, and it's still being developed. ARM has also support for vectorization. Their extension, the most famous one is Neon. I'm sure many people have heard about it, and Intel has 3 types of extensions. SSE is the oldest, AVX is the one that most CPUs nowadays have, and there is a third one which is mostly used in server systems. So as far as compiler does vectorization for you, and it can take advantage of available SIMD instructions. But this works only if you provide the proper compilation flag to the compiler. So you need to give the compiler O3 on GCC, or CLANG vectorizes also with O2, and you need to provide a proper architectural flag. So if the compiler doesn't have good architectural flag, it might generate vectorized code, but which is less efficient. Okay, so this is about autovectorization, and if you're interested, so if you are debugging a certain loop and you're interested whether the compiler vectorized that loop or not, all compilers, all famous compilers have a compiler vectorization report, and you can generate them with these flags, fopt-info, optall on GCC. These are the flags here for CLANG, and the third ones are for MSVC. I think all compilers nowadays have flags that will show you vectorization report. And here is the CLANG's report here. I generate for some of my code, and then you see something like here, something like this. Remark, the cost model indicates that vectorization is not beneficial. So the compiler has certain cost model, and it can decide that vectorization is not worthy, and then it will emit scalar code instead of vectorized code. But for some other loop, it can say, for example, this one, it says remark vectorized loop, which means that the compiler's cost model told him that vectorization pays off, and it vectorized the loop. So the vectorization, the usefulness of vectorization report is, I don't know, I wouldn't put it as very useful, because it doesn't tell you exactly what's the problem if the vectorization fails. So if you're, let's say, if you are inexperienced with vectorizing, with auto-vectorization, it is very difficult to get to speed up your loop by just looking in the vectorization report and figuring out what you need to do. And that's why you're here. So today we'll learn what are common vectorization inhibitors that prevent automatic compiler vectorization and how you can get rid of them. We cover error messages from CLANG's report. GCC has a different report. It looks different. In my opinion, CLANG is a bit better. It's more readable, but I mean, many people in embedded use GCC, so that's also an option. So with regards to vectorization inhibitors, as I said, these are things that inhibit vectorization in the sense either they completely prevent it, so no automatic vectorization is possible, or they make the vectorized code less efficient. So that's also a certain type of inhibitor. So let's go. So if you have this, if you get this message from the vectorization, from the compiler vectorization report that says the cost model indicates that vectorization is not beneficial. One of the reasons why you might get that message is because you have non-sequential memory accesses in your loop. So what are non-sequential memory accesses? So when the CPU processes data, it sees normally data is stored in some kind of arrays. Arrays of floats, arrays of doubles, and so on. And the CPU iterates over that data and collects data and performs some kind of work with it. Now, when we are developing software, we can analyze what kind of memory access pattern a certain pointer has, how it develops while the loop is running. And there are typically 4 memory access types. So there is a constant memory access type, which is when the code is accessing the same memory location over and over. Now, typically what happens is that the compiler will optimize this. Unless there is some kind of problem, the compiler will optimize this and this will be in a register. And this is the fastest type of memory access. Second, the type of memory access are sequential memory accesses. This is when the program is hitting sequentially memory addresses. So if you have an array of floats and you access A0, A1, A2, this is sequential memory access. Now, strided memory access is that the program is accessing memory addresses with a fixed stride. So imagine A0, A2, A4, A6, that's strided memory access. And strided memory accesses happen a lot when you have like arrays of classes. Because like, if the class is 16 bytes and you are accessing the element at position 0, which is 4 bytes, so you have a stride of 16. So there is an element that you're piece of data that you're accessing. There is some data that you're not accessing. Again, some data that are accessing and so on. And finally, there are random memory accesses. Random memory access just the CPUs all over memory looking for collecting data all over memory without any specific pattern. So if you want efficient compiler autovectorization, you should strive to have all memory accesses either constant or sequential. Strided and random are also possible to vectorize, but depending on the architecture, so they might not be efficient, and compilers generally omit vectorization in those cases. Okay, so let's do a memory access pattern analysis of this loop. So I have a loop here, and the question is, when I do memory pattern access analysis, I'm always looking at the innermost loop. So this is the loop that goes over J. And I ask myself, what happens when J increases by increment? So let's see, what happens when J increases by 1? What happens to this pointer out? So increases by 1. When J, instead of J, we write J plus 1. This pointer just increases by 1. And what kind of access pattern is that? Sequential, yes. Okay, what is the access pattern of the second here, of the second pointer? So J times N plus I. Strided, yes. So when J increases by 1, the next element is N positions further away. Okay, what is the access pattern of this index of J? Sequential, yes, because it depends on J, linearly or sequential. And the access pattern of histogram of index of J. So what happens when J increases by 1? This index of J, Yes. So the index of j is a random value. We don't know. Generally, we don't know what's inside, and so this access to histogram is the compiler will consider it as a random memory access. So this is memory access pattern analysis, and this is important to understand what's going on and why the compiler doesn't vectorize a certain loop. So in certain cases, you can fix memory bad memory access pattern. One of the ways to do it, if you have nested loops, so I have here nested loops, and one of the ways to do it is to perform loop interchange. When I move the loop that was originally the inner loop, I move it outside. So you see here that the loop over j is outer loop, and loop over I is the inner loop. So this is loop interchange. Now let's analyze again the memory access pattern. So this time the innermost loop is over I. So what happens to out of I times n plus j? What is the memory access pattern for this variable? Strided. Okay, and for this one? Okay, and for this one, index of j, constant. And for a histogram of index of j, constant. Okay, so we have two constants, one sequential and one strided. And originally we had one strided, two sequential, and one random. And generally, in terms of memory efficiency, this second loop is much more efficient compared to the first one. There is another example here. It's a matrix multiplication. So what happens when I put the outer loop over k to be the middle loop and exchange the second, third loops? So let's do the memory access pattern analysis here. So what is the memory access pattern for C of ij? So the innermost loop is over k. Constant. This is constant and this is constant. So generally compiler can move those accesses to register. So what is the memory access pattern of A of ik? Sequential, and this one strided. Yes, because B of kj, there is a certain stride here. Let's analyze this second loop after the interchange. So what is, in this case we have an inner loop which goes over j. So what is the access pattern of C of ij? Sequential, and this one A of ik, is it strided or is it constant? It's a constant because j increases by 1, but j doesn't figure in this expression. And finally, this one, this sequential. So we have three sequential and one constant. And originally we had two constant, one sequential, one strided. And actually, when it comes, if you write it like this in the compiler, it would probably not vectorize it. It would say the cost model error. But if you rewrite it like this, because all accesses are either constant or sequential, this thing will get vectorized. Okay? Yes?
Can the compiler not do a loop interchange?
The only compilers that actually do that are compilers that are used for these huge scientific mainframes. The only one that I see was some NEC compiler that was used in a very specific. GCC and CLANG do not do this kind of optimizations. In principle, they can do it, but they don't do it. Okay, so this was about loop interchange. So this will allow to vectorize the loop in the sense that the compiler will emit vector instructions, but this vectorization will not be the most efficient, and there are additional steps that you will need to make sure that vectorization is the most efficient if this is your goal. Okay, let's do some advanced loop interchange. So look at this loop here. So I have a loop. This loop, imagine you have an image and it calculates the average of each column in the image. Okay? So this is sum, initializes to 0, then it goes over columns, and then it calculates the out of W. Now question is here, the access pattern to sum is constant, and the access pattern to image is h times width. When h increases by 1, this is strided memory access pattern, and generally compiler will complain about the cost model. Now, loop interchange is an interesting thing that we can investigate here, but the question is, can we do it? Yes, we can, but there is a catch. So this float sum needs to become an array. because something will change. So here is on the left is original loop. Now, instead of having this sum as an array, I'm reusing out of W. So imagine I rewrote instead of sum here out of W, so it doesn't change anything. So what happened is here is that I split this original loop into 3 loops. So this is the first loop that initializes this sum. This is the loop that calculates this this average, and finally in the middle is the original loop. So this loop, and you see there are nothing before and nothing after it. Okay, let's do the memory access pattern analysis this time. So originally it was constant and strided, and now out of W is what kind of memory access pattern? Sequential, and image of h times width plus W. Yeah. Yes. So sequential, and this compiler can actually vectorize this. Okay, so this was about loop interchange. Do you have any questions? Okay. The next topic about memory efficiency and memory access pattern are these non-sequential memory accesses are when it comes to classes. And I'm going to talk about what is the layout of my bar array, in the sense, how is it stored in memory? So it's stored like this. So I have foo, I have a struct foo with elements x, y, z, and I have bar which has 2 instances of foo, and the layout is like this: foo 0x, foo 0y, foo 0z, foo 1x, foo 1y, foo 1z, and then keeps repeating. So when it comes to vectorization exists for floats, for integers, for doubles. It doesn't exist for classes. In underlying compiler, the CPU works with floats and doubles, or integers or whatever. It doesn't work with classes. So classes are just an abstraction above those simple types. And this kind of code is typically not vectorizable, because when you are doing vectorization, you want to process foo 0 of x, and then next element of foo 0 of x, then next element foo 0 of x in the same way. You want to have different processing from foo 0 of x and foo 0 of y. So sometimes you want to have the same type of processing, and most of the time you don't want that. And for that reason, vectorization, the compiler will complain about the cost model. Now the solution here is, you probably heard of it, array of structures. And today, if you were in Vittorio Romeo's lecture, he was talking about data-oriented design, and he was talking about, one of the main premises of that approach is convert everything to structure of arrays, so make everything arrays of simple types and let the compiler optimize it. And that's the essential, the thing that is behind this approach. So the previous layout was called array of structures, and very common in object-oriented programming. And probably the biggest woe of people who work with hardware with object-oriented programming is that object-oriented programming, if you have large classes in containers, can be very inefficient, because you're just accessing one piece of data or 2 pieces of data in a large class, and the CPU is transferring data from the memory to the caches, and a lot of that gets wasted. So how is this array of structure? What can we do to fix this? We changed the memory layout to struct of arrays. So originally it looked like this. And now instead of, originally we had float x, float y, float z, and then 2 instances of foo. And now for each member of foo, I have a dedicated array. So I have one array that holds x's, another array that holds y's, another array that holds z's, and then I have 2 instances of this foo SOA. And what happens then is that each array is separate, and then these are just arrays of floats, and vectorization just goes. The compiler doesn't complain, cost model is happy, and everyone's happy. Yeah, so any questions? Yes?
Do math libraries like Eigen do this by default?
I don't know. So I never used Eigen, so I don't know. Maybe somebody from the audience know. No. Okay. So matrices are typically just like arrays of floats or doubles, whatever data types. They're not array of classes. as far as I understand. Okay. So then second is, again, the cost model indicates that vectorization is not beneficial. You get this message. And the question is now, what's the problem now? And that means that inside your loop, you have too many conditionals. Now, conditional execution inside loops make vectorization less efficient. And generally, when you remove conditions, you get rid of conditions, you decrease the number of conditions. That generally helps both vectorization, but even if the vectorization doesn't happen, it helps the performance of software performance. Why are conditionals problem with vectorization? Well, when you have conditional processing, what happens is that you load A0 and you do some kind of processing, then you load A1, but you do different kind of processing, and then you load A2, then you could do maybe some kind of third kind of processing because you have this if else, and so on. But with vector, you're loading 4 and you need to do the same type of processing of all 4. You cannot like multiply the lane, the value 0 and do addition on value 1 and division on value 2. It doesn't work like that. So it has to be the same type of processing. And for that reason, if you have conditions, generally that decreases the efficiency of vectorization. So what can we do with what can we do to fix this? So look at this loop here, and look, I have here two arrays A, B, and N, and inside loop I have this if B of I plus equals 1. So one types of loops conditions are called loop invariant conditions, and they're called loop invariant because they don't change their value while the loop is running. They're in the scope of the loop, they're constant. And what happens then is that this B, which is a parameter to this function, is constant, doesn't change value, and essentially the compilers do get rid of this. So this transformation is called loop unswitching. Compilers do it, but there is a catch there, is that every time you do this transformation, the size of your code grows. So here is how it looks like. So here is my original function, and what either the compiler does or I can do myself is that I move this condition outside of the loop, so if B, and then if the B is true, then I have this loop that inside has this B of I plus equal 1 without any conditions. And if the B is false, then I have here A of I plus equal 1, and B of I is completely gone. Okay? And this is one. So all the loop invariant conditions are candidates for the removal from the loop. The compilers will do this, not always. Sometimes they do it, sometimes they not. If you have a lot of conditions in the loop, like 3 or 4 conditions, even though the loop invariant compilers just says like the code would be too big and I will omit loop invariant, removing loop invariant code motions, called that transformation, or loop unswitching. Any questions? Okay, so the next are called iterator dependent conditions. So these are different kind of conditions, and you see here on the right side, you see here I equals j. So these the conditions, they either depend on constants or they depend on iterator values. So what's so special about these conditions is that these conditions are predictable. You know at exactly which iteration this condition will be true and which iteration this condition will be false. And then you can, because you know that, you can remove this using various techniques, like in breaking the loop into 2 loops, or maybe loop peeling, removing a few iterations at the beginning of the loop or at the end of the loop, so everything works. And here is an example how I removed the loop iterator dependent conditions from this loop. So what happened is there are two ways. So the first way is that I just do B of ij equals A of ij, the else body here without the if, and then outside of the loop I just set the if, the specific case where E equals j. So that's one way to do it. Another way to do it is to have 2 loops. The first loop goes from 0 to I, and the second loop goes from I plus 1 to n. And you see inside this loop and this loop there are no conditions, and I have this special case where this is the time I know that the I is equal j, and I can perform this kind of transformation. Any questions? Okay, the compilers, as far as in my experience, they don't do this kind of optimizations, so you would need to do it yourself manually. The next thing you could do is you could simplify loop body. So every time you have a condition, and inside the condition, imagine you have a condition if, and you have else, and there's some certain in if part and in else part. Everything that you can move out of if and else and move it outside of if else, so it is common to both, that improves the efficiency of vectorization. And here is one example here. So if my piece, so this is a real condition. It's not loop invariant. It's not iterator dependent. It depends on the data, and we do not shape the data before we run this loop. So I say here, if the a of I is greater than 0, then b of I equals a of I plus a of I. Otherwise, b of I equals a of I times a of I. So what happens here is that I can simplify this condition. So instead of having one multiplication and one addition, I can conditionally load either constant a of I or 2, depending on the value of a of I. And then I multiply with this value. So multiplication by 2 is just addition to itself, and this is the other one is multiplication by itself. Okay, is this example clear? Okay, any yes?
Why double?
Sorry?
Why double type?
I don't know. Just no reason, not specific, because there were no types here. So, and I had to write the type here. Okay. The next thing is loops with low trip count. So trip count means small number of iterations. So loops trip count is number of iterations. And look at this loop here. So what happens? Why is low trip count a problem? Low trip count is a problem because if you have 3 iterations and your vector size is 4, essentially you are just wasting place in a vector. So what happens here? So here is a loop here, and this loop initializes this a of I times 3 plus j to 0, but it has only 3 iterations. And vectorization might not happen here, or maybe the compiler used some kind of tricks, but yeah, it might not happen. And can we do something about it? Actually, we can. One way is loop collapsing, which means that I collapse these loops into one loop. So something like this. So on the left side, I had a of I times 3 plus j equals 0. But here I have only one loop, which goes from 0 to 3 times n. Now, collapsing is not always possible. It is useful technique for vectorization, but it's not always possible. Yeah, so this is one way to fix it. Another way to fix it is with loop interchange. So here on the left, this is a Gaussian smoothing filter. I have my code. Its night is optimal, but this kernel size is 5. And vectorization is here just not efficient. So what can I do is I can perform loop interchange with loop interchange like this. And then what happens is that suddenly my loop doesn't go from 0 to kernel size to 5, but goes to 0 to width minus kernel size. And if width is 600 minus 5, that's 595. So I get this. Now the thing with loop interchange is that if you get bad memory access pattern, then you're worse off. So in this case, this doesn't happen because the access pattern for some is constant. This one has a sequential. And this one has a constant also. Yeah. But on the other hand side, this one has a sequential, this is a constant, and this is again sequential, so we're fine here. Another way to, so with regards to low trip count, this is what you can do for the compiler. There aren't any things that you can do to compiler, but if you do manual vectorization, there are things that you can also use with manual vectorization to vectorize loop with low trip count. Any questions? Okay, so next are loop carry dependencies. You get a message saying loop not vectorized, unsafe dependent memory operations in loop, or loop not vectorized, value that could not be identified as reduction is used outside the loop. Now, these loop carry dependencies, there are 2 types of dependencies. Dependencies that are real. and dependencies that the compiler think that might be dependency, but in reality there is no dependency. And yeah, we'll cover both of them. So does everybody know what a loop carry dependency is? Does somebody does not know? Okay, loop carry dependency is when you have a loop, and in order to calculate the data for this iteration of the loop depends on the data coming from the previous iteration. And why are these important? This means that you can run the loop only from beginning to end. Ideally, loops that are good, vectorizable, parallelizable, whatever, can be run from beginning to end or from the end to beginning, or you can do any way you can run them and it will work. But loop with loop carry dependencies, they don't work like that. Now, loop carry dependencies in the theory of computations, these are like the main instruction dependencies are the main things why computers cannot just. You can add a lot of hardware, but doesn't get faster. So this is the essential thing that is slowing down computations. So here's one example of loop carry dependency. So this is prefix sum. And I see here that out of I equals out of I minus 1 plus in of I. So in order to calculate out of I need out of I minus 1. And in order to calculate out of I minus 1, I need out of I minus 2. Another is this copy of greater algorithm. So dependencies over J, because this J is unpredictable. Sometimes increases, sometimes it doesn't increase. So you need to run your loop from the beginning and run it like this. So these two loops, compiler does not vectorize them. They're, as far as compiler is concerned, not vectorizable. Now, as far as fixing issues with loop carry dependencies, there isn't a lot of things that you can do at compile time. With automatic compiler vectorization. There are some tricks that you can do with manual vectorization. And that's it. So one of the techniques you can use to vectorize loops is if you have a loop that doesn't vectorize, but you think like vectorization could be useful here. So you can remove them with loop fission, or CLANG calls it loop distribution. So what is loop fission? So imagine here this is my loop and I have this complex calculation, and I know this complex calculation would really profit from vectorization. It might be like cosine or arcus tangens. But I have the last statement here has this loop carry dependency over J, and I cannot vectorize this loop. So what is the idea? The idea is to split this loop into two loops, one which is vectorizable here, and the other one that is not vectorizable, this one here. So vectorizable loop, I store the result of the complex calculation to a temporary array S. And then in the non-vectorizable part, I reload S and then do the comparison and then update whatever is needed. So that is why one of the ways, probably the way of least resistance or least thinking. So this is the way how you can vectorize partially some loops. CLANG supports also this with a pragma. It's called distribute. Pragma CLANG distribute something, and it will try to split the loop into two loops. Okay. So here I removed these loop carry dependencies, but you can remove other stuff as well. Like here I remove this random memory access. So instead of having random memory access, I'm writing this result of complex calculation to temporary array. And then here I load from the temporary array to this B of index of I, which is the random access. Okay, any questions? Okay, so yeah, you can also use loop fission to remove like complex conditions. So it's a very versatile technique, especially if the loop is big and you have like what to remove. Generally, other techniques like are more efficient than loop fission. And with loop fission, you get the problem that you're iterating over the same data 2 times. So when you're iterating over the second times, you're not getting the data. Originally, you were getting the data from the register, and now you're getting somewhere from the memory subsystem, and not necessarily from the fast part of the memory subsystem. It can be like from the memory, which has large latency and low bandwidth, so you will be limited there. Yeah, so yeah, that's about loop fission, removing through loop fission. The next thing that compilers do is this their own idiosyncrasies, their own like weird behaviors. It will say like loop not vectorized cannot identify array bounds, or loop not vectorized cannot prove it is safe to reorder floating point operations. So what is about that? Well, in some cases you look at the loop and the loop is like perfectly vectorizable, and you're like mad at the compiler, why are you not doing this? And the reason the compiler tries to maintain C++ correctness, so the compiler needs to ensure correctness first and speed after that, and then it can simply like omit vectorization completely. The one thing is pointer aliasing. Why the vectorization doesn't happen is when you have vectorization. So imagine like here is my loop, and it has six pointers. Now, if these pointers are completely like separate blocks of memory, A points to one block of memory and B points to another block of memory and C to another, then vectorization is fine. But you can call this function like test with x, x plus 1, x plus 2, x plus 3, x plus 4. And in that case, this code has loop carry dependencies. Now, for you, when you look at this code, like say, there are never loop carry dependencies, but the compiler doesn't know that, so it will omit vectorization. Now, compilers typically have this pointer aliasing analysis. Like if you have, imagine you have one buffer and two buffer, so one pointer and a second pointer. So from those pointer, it tries to determine what is the size of the block that the pointer is pointing at, and then it tries to determine if those blocks overlap. But this pointer aliasing analysis works for 1, 2, or maybe 3 pointers, because with a large number of pointers, you need to check every pointer with every other pointer. So there are a lot of checks, and then the compiler omit vectorization, like in this case. If you know for sure that these pointers are pointing to a block of memory, they're the only ones that are pointing to that block of memory and no other, then you can use a restrict keyword, which is part of C++ standard. No, is it restrict part of C++ standard? Is C, okay. But all compilers have some kind of restrict in C++, at least in my experience. And you can just mark those as restrict, means I'm the only one showing with that, pointing to this block, don't do any analysis. But if you do stuff like this, then you get the bad results. Okay, so the last thing is that some loops, notably loops with reduction, produce different results when they're vectorized. So what happens here? I have this double and I sum it to this value, but because of the way the vectorization works, the result will be slightly different. And the compiler wants to ensure that you get always the same results, and that the result is if you compile the same code on another compiler, you get also the same results. And in that case, it avoids vectorization with doubles and with floats, but not with integer and with integers. Now, the reason is that floating point is not associative, so a plus b plus a plus b, then plus c. It's not exactly the same as a plus b plus c. So that's the reason. Now, if you want to force vectorization, you can use like a pragma, like pragma CLANG loop vectorize, or you can pass to the compiler f associative math or f fast math, and then the compiler will vectorize this loop and won't complain. Any questions? Okay. So what happens here? If you manage to convince the compiler to vectorize their loop, then congratulations. If not, the further step is manual vectorization. And simply, like compilers, there are certain types that the compilers do not vectorize for one reason or another. For example, they don't vectorize while or do while loops because while loops can access data outside of allowed memory. For example, loop with loop carry dependencies, which are generally not vectorizable by the compiler, but they're vectorizable with some tricks and with manual vectorization. Loops with low trip counts, so again, they can be vectorized with manual vectorization and so on. Okay, so that's it, guys. I don't know how much time do we have. Oh, okay, so yeah. Any questions? Yes? This gentleman here.
For the amount of loops that you do with low trip count, when you have what's it called, non-aligned loops, is that
What is a non-aligned? There is a non-aligned data, not a non.
not aligned data? So
Okay.
extra, would it be better to manually make sure the data is alignable, or is that something?
So alignment nowadays, alignment is not that big of a problem. In general, in my experience, whether data. So when you say alignment, there can mean two things. There can be vector size aligned, which is, for example, on AVX 256 byte, or natural alignment like float is 4 byte aligned, or it can be 1 byte aligned. So you're reading. For vectorization. So if you're all the architecture support unaligned access to data. I mean, you can access with the vector instruction 4 byte aligned floats. This will work, and compilers will not complain. The hardware will not complain. You might get a slight penalty, but nothing huge. So yeah, vectorization will probably pay off even in that case. More questions? Okay, guys, thank you for coming and enjoy the rest of the conference.